All right, welcome everyone. Today we're going to talk about the scientific method. It's Unit 1, Notes 1 continued. So if you're following along with the guided notes provided on Canvas or you have a printout, it is simply starting on page 3. So we've done already page 1 and 2 talking about the nature of science and covering this flowchart right here. So what we're going to do today is talk about the scientific method, probably something you've talked about in middle school and maybe even elementary school, but definitely something that you're going to carry forward throughout all of your sciences that you take forward. It is something that even adults follow very religiously, and that's why it's so important to talk about the scientific method. And then we'll talk a little bit about scientific laws and theories and do some practice problems and maybe do an example or two about the scientific method. So without further ado, let's go ahead and jump right into it. All right, so the scientific method has a lot of different steps, and these steps have to be done in order to have a successful experiment so that we could learn more about the natural world and have reliable data. So we're going to go through these steps one at a time, but first I'm going to go ahead and just kind of minimize myself here in the corner. That way you can see all the slides. The very first step of the scientific method is going to be state the problem. You're going to identify something that is wrong. You're going to try to figure out, okay, what could possibly be going on here. Something has to be going on that you want to figure it out. It might not necessarily be a problem, but it's definitely something that you want to learn more about. So that's kind of the problem, is that you want to learn more about it. Next is that you want to gather information, gather as much information as you possibly can. It could be previous knowledge that you already know from your previous science classes or whatever you've learned just from experience. And then you want to gather as much information as possible to kind of come up with an educated guess. And we have a word for that educated guess, and that is a hypothesis. All right, so we're going to go ahead and form a hypothesis so that we can kind of guess what's going on and maybe create an experiment from that hypothesis. So the next step is to then test the hypothesis, and that's where we're actually going to design the experiment, do the experiment, and then collect our results afterwards. So that's analyze your data, you've collected your results, and now you're taking a look at your data. And when you take a look at your data, it could be something really simple, it could be very complex, it could take a long time, it could take, it could be instantaneous that you look at your data and say, oh, this doesn't support my hypothesis. I have to gather more information, or oh, I figured out the problem and now I can move on. So when you analyze the data, there's really two ways you can go about this. You can analyze the data, and the data either does not support hypothesis or it does support the hypothesis. Okay, so when it does not support hypothesis, you'll notice on the left side, we want to modify and retest, form a new hypothesis, retest that, create a new experiment on that, and then analyze the data. And then if it does support the hypothesis, then we kind of figured out an answer to our problem. So the scientific method, it may seem kind of complex, but it is something that we do on a daily basis without even thinking about it. I just realized here I'm kind of in the way, so I'm going to go right there. Um, so an example that I can give you for the scientific method is something that just happened to me this morning. Let's say I want to plug in my phone to charge it because my phone is like at 30 something percent. I probably need to have a little bit of charge for the day, so I'm going to go ahead and plug it in. So I go over to where I typically plug in my phone, plug it in, and it's not charging. I look at the phone, cords are in, it's not charging. So I stated the problem. The problem that I have here is that my phone is not charging. So now what I'm going to do is gather information. So what I'm going to do is kind of take a look. Is the phone plugged all the way in? Yes, it is. Is the other end plugged into the charging block? Yes, it is. And is the charging block plugged into the outlet? Yes, it is. Okay, so I've gathered information. So now I have to form a hypothesis. And my hypothesis has to be an educated guess. All right, so it can't just be a random guess, and it has to be something that is, educated from the information I've gathered. A random guess would be like, oh, my phone's not charging because today's Wednesday, and my phone just doesn't charge on Wednesdays. That's not an educated guess. That has to be something. It has to be tangible. It has to be relatable to the information that we've gathered so far. So an educated guess might be, maybe the outlet's broken, maybe the charging block is broken, Maybe the cord is broken, or even my phone is broken, the charging port on my phone. So those are all possible hypotheses that we have, and that's based off of the information that we've gathered. So let's say we form the hypothesis, and in this case, the hypothesis is going to be the charging cable just simply does not work. Okay, so I'm going to go ahead and test the hypothesis by maybe getting a different charging cable. I can go to a different part of the house and get a different charging cable and plugging it in. All right, but the important thing that I want you to remember is that I cannot replace both the charging cable and the block. I can only replace the charging cable. And what I mean by the block is that the part that goes into the wall. So I have to replace only the charging cable. And when I do that, then I can test to see if it's the charging cable that's broken or if it's the block that goes into the wall that's broken. So if I'm replacing only the charging cable, I can test for that. So I replace the charging cable, and let's say, for instance, I've analyzed my data and it still doesn't charge. So in that case, I'm right here. I've analyzed my data. I haven't really, I haven't written anything down. Nothing's written down, but I'm going to conclude that my hypothesis is not supported. So then I have to modify it and retest and say, okay, if it's not the charging cable, it must be the block that is broken. And so when I plug in the phone with the new block into the wall, voila, my phone is charging. And so I've analyzed the data, and the conclusion does support the hypothesis. Now that's a hypothetical situation for me. It was actually that I just didn't plug in the block into the wall far enough. But that's a great example of how we use the scientific method on a daily basis without even thinking about it. Something's wrong. Let me figure out what it is. Come up with a logical, realistic, educated guess as to why something might not be there, and then figure it out. So another example is, let's say you're looking for your favorite jacket on your way to school. You can't find it. It's not in your regular spot. It's not in your bed, or on your in the coat rack. So you state the problem, gather information, you look around to see where it is, and then you think about, where did I put my jacket? You form a hypothesis. Oh, I actually never left it, or I never took it out of the car. I left it in the car yesterday. So you test the hypothesis. You go check. Is it in the car? Yes. You've analyzed the data just by visually seeing that the jacket was in the car. Your conclusion supports your hypothesis. Easy stuff like that. We do it on a daily basis, where we state the problem, gather information, make an educated guess with a hypothesis, test it, and then analyze the data. That's basically what the scientific method is. It can be really simple as that, or it can be extremely complex if you're doing like really sophisticated experiments. So once again, it's very important to cover the scientific method, because this is a very organized way to make sure that our data isn't skewed and that we're actually doing proper science. One thing that I didn't mention before is that if we are doing an actual scientific experiment where we want to learn more about the natural world or outer space, if we conduct an experiment over and over again and we get the same results every time, where we get the same data and it supports a specific hypothesis, then we can form what's called a scientific theory. And a theory has to be from an experiment that is done maybe dozens of times, possibly hundreds or even thousands of times, and consistently get the same results. And it has to be something new, where we kind of are learning something about the natural world. One example of a scientific theory that we have received from multiple tests is the theory of gravity. Now, gravity is both a theory and a law, and we'll talk a little bit about the difference of that. But if I were to take a tennis ball and just drop it from shoulder height 1,000 times, 1,000,000 times, every single time I'm going to get the same results, where the ball just hits the ground and then bounces a little bit. So it's always going to be attracted towards the ground. So because I've done that experiment over and over again, where I'm just dropping a tennis ball and analyzing what happens to it, I've gotten the same results every single time. I could then form a theory that there is an attraction between two objects. All right, so moving forward, let's take a look at the difference between a scientific law and a scientific theory. So a scientific law is the prediction of what happens. Oftentimes when we have a scientific law, it describes a pattern in nature. And one note that I might not have here, actually I do have it, is that laws are universally stated as mathematical formulas. Usually a scientific law is mathematically proven. So when we're talking about, for example, the law of gravity tells us, when a rocket ship is going into outer space, how much gravity is being influenced by it. You can do mathematical calculations. Or if an object is in free fall, like let's say a skydiver jumps out of an airplane, we can calculate their speed based off of the gravity of the Earth. So that's done with math. So scientific laws are tied in with math. So if you want to highlight or underline the word mathematical formulas next to scientific laws, that'll help you remember that a scientific law has to be mathematically proven. Now, scientific theory is going to be a little bit different, and the scientific theory is going to explain why something happens. Okay, so we know that gravity exists. So we know that gravity attracts two objects together, and we can actually calculate with mathematical formulas the attraction between two objects depending on their size. Now the theory is, why does that happen? Why do two objects attract one another? So it's based off of many observations and experimental results, and we're getting into really different fields here, like physics and astrophysics and things like that, on why does gravity exist. You have to be able to predict the results, and not all theories can be proven with math. So a scientific theory that it can be proven with math is then made into a scientific law, but a lot of theories don't have math behind them, so they stay as theories. But you should be able to predict the results based off of those theories. With further exploration and further experimentation as technology increases, we could change over time. As more tests and experiments are performed, the theory can change significantly as technology advances and more tests are done. So that's something to keep in mind. Theories are not really like cemented. They are not really something that cannot be changed. They definitely can be changed, unlike a law, which is proven mathematically. Laws are really hard to change. They typically don't. An example, besides the gravity one, is the kinetic theory, which explains why liquid water under 32 degrees Fahrenheit becomes solid, but also why a saw blade gets hot when used. So the kinetic theory describes the transfer of heat from one object to another, or one atom to another atom. So that's the kinetic theory. So both scientific laws and scientific theories are open to challenges and testing. Like I mentioned before, though, scientific laws are really, really hard to disprove just because there is math behind them, and they can be, they're kind of like more cemented with math. The theories, not so much. They are reliable for the most part, but with better technology and better understanding of the natural world, they can be challenged, and we can revise them. Some of them are only valid under certain circumstances. For instance, specific laws in physics really only apply to Earth, but if we go into like outer space and start dealing with like really big objects like black holes and things like that, those laws might not exist as much. So just something to keep in mind, that only under valid circumstances do things exist. All right, so in our notes, we've got, I'm going to go ahead and hide here so that we can see all of the problems. Practice problem number 5. Go ahead and spend about 5 minutes filling this one out, this matching section, and then when you feel like you've gotten all the answers, just go ahead and wait patiently until we go over them in a little bit. So go ahead and pause the video right here so that you can work on this problem. Okay, so let's go ahead and go over the answers for practice problem number 5. Number 5 says, in the space provided, write the letter of the description that best matches each term or phrase. So I am going to start with number 1, which is science, and I felt that letter C was the best for describing what science is: observing, studying, and experimenting to find the nature of things. Number 2, which is technology, is A, the application of scientific knowledge for practical purposes. Number 3, model, is H, a representation used to study an object or event. Number 4, scientific law, is letter E, which is an explanation of how a natural process works. Some of you might have put the letter I instead, but that actually applies more to a scientific theory. So E is number 4, and I is for number 5. A scientific theory is a description of a process in nature that can be tested by repeated experiments. For number 6, chemistry is going to be D, a branch of physical science that studies matter and its changes. Physics, which is what we're going to cover next semester, number 7 is the letter J, a branch of physical science that studies forces and energy. Number 8, geology, is going to be the letter B, a branch of earth science which studies the physical nature and history of the earth. Number 9 is going to be letter F, a branch of earth science which studies the atmosphere and the weather. And by process of elimination, last but not least, is ecology, letter G, a branch of biology which studies the balance in nature. All right, so what I would like for you to do now is take one more minute to answer practice problems 6, 7, and 8. I have to warn you, though, that problem number 6 does have multiple correct answers, so circle all that apply. Number 7, however, only has one correct answer, or one best answer, I should say. So only circle 1 for number 7. Go ahead and spend about 1 minute. I'm going to pause here so you can answer those questions. Okay, so number 6, which says a scientific theory is an explanation that does what? A says has been published in a journal or book. B predicts what will happen. C has been tested by many observations. Or D, a scientist has tested with an experiment. Well, A does not necessarily have to be true. It does not necessarily have to be published in a book. So the A is not correct. However, a scientific theory will predict what will happen. So answer choice B is correct. A scientific theory will or has been tested by many observations over and over again. So C is correct. And a scientific theory is something that a scientist probably has done with an experiment as well. So the answer choice D is correct as well. So B, C, and D are the correct choices for practice problem number 6. For number 7 says, for a scientific theory to be valid, it must allow you to do what? Perform experiments, form a hypothesis, obtain new results each time, or make predictions. You do not need to you do not need a scientific theory to perform experiments. You could just do that on your own without a theory. Same is true with forming a hypothesis. You don't need a scientific theory to form a hypothesis. And for letter C, if you got new results every single time you did an experiment and it's the exact same experiment, that's the exact opposite of forming a scientific theory. A scientific theory should be able to predict what happens. So if you're getting new results, it's impossible to make predictions. And so answer choice D is the only one that is true, making predictions. A scientific theory should be valid if it can make predictions. Finally, number 8 here, a possible explanation to a scientific problem is called a blank. I would have accepted educated guess, but the word I'm also looking for is hypothesis. So a possible answer to a scientific problem is a hypothesis. All right. Moving forward, how do we test a hypothesis? So this is where we're kind of getting into the really nitty-gritty details of how to do an experiment properly and to make sure that the experiment is ending up valid at the end, because a lot of times people will try to do an experiment, but the results will be inconclusive because the experiment itself was invalid. So we got to make sure that we are doing a valid and correct experiment so that we can make sure that we are getting decent results here. So one common way to test a hypothesis is to, of course, perform an experiment. And an experiment tests the effect of one thing on another using controlled conditions. And the word I really want to focus on this slide here is one thing. So when you do an experiment, you're only testing that one thing. It is very, very crucial that you only test one thing at a time. You can test multiple things, but they have to be there. Each thing that you're testing has to be its own separate experiment. Okay? And so when we test a hypothesis, we also have these things called variables. And a variable is a quantity that can have more than a single value. And so we'll talk a little bit about that in a little bit. But an example that I can give you is like, let's say we are testing which type of plant food is helping my plant grow the best. Well, the variable that you're going to be testing is the height of the plant, because it is something that can have more than a single value. You can have a plant that is, let's say, 1 inch tall, 2 inches tall. Let's say it could be 2 feet tall. So that's more than one single value. So the height of the plant in that case would be the variable. Speaking of which, we're actually going to take a look at that specific scenario and kind of do this hypothetical experiment. So you imagine that you want to see which of the three fertilizers helps plant grow the best or the biggest. So let's say you went to the hardware store, you got three different fertilizers because they have three different brands. You want to see which one helps the plant grow the biggest. To set up the experiment, you have to consider the possible factors that will affect the plant growth. So just thinking about like what do plants need in order to survive? Well, they need water. They also need sunlight. They need to be in some type of dirt conditions. Um, Everything else really needs to be the same. The other thing we need to consider here is that if we are testing different types of fertilizer on plants, the plants that we are growing have to be the exact same plant. There are plants that grow very slowly and there are plants that grow very quickly. I know, for example, like if you try to grow vegetables, some vegetables grow very quickly and some grow very slowly. Like let's say a carrot would take pretty long to grow, but let's say you're growing also bamboo. Bamboo grows sometimes an inch or two a day, so it can grow very quickly, um, possibly even more in really rainy conditions. So the plant that you are testing has to be the same plant so that you're making a fair comparison between the different fertilizers. So right now what we're going to do is just analyze this graph, which is, let's say we've done the experiment, we've kind of prepped it for it, and we have four different plants and we've labeled them A, B, C, and D. And the amount of water that we are giving them is going to be the same. You might notice that it's the same every single box here, 4 ounces every 3 days, and that's true for every single plant. The amount of sunlight is also the same every single day. It's 6 hours per day. The only thing that is different is the fertilizer type. So let's say we gave plant A fertilizer A, plant B fertilizer B, plant C fertilizer C, and plant D we gave no fertilizer. Okay, so there's a lot of really important things going on here. So we're going to talk about each one of them. The reason why the amount of water is the same for all four plants, and the amount of sun is the same for all four plants is because if it wasn't, how would you know what is affecting the height of the plant? Was it the amount of sunlight or was it actually the fertilizer type? You couldn't say definitively which one it was, so that means you have to keep all of these things the same. There's a specific word for that, for these things that are remaining the same, and that is a controlled variable. And controlled variables, there are things that can change. Remember, a variable is something that has a value that can change. So if I really wanted to, I could change the amount of water that I give these plants every single day. I could limit how much sunlight they get. I could change this to 4 hours a day if I really wanted to. So those are variables. A variable is a number that can change. But because I am under control of what's going on here, that is a controlled variable. And I am making sure that all of the controlled variables for all of the plants are the same. And so again, we're doing that because we want to make sure that we are limiting the height of the plants to being just what the fertilizer is. And one more thing before we talk about these red and yellow terms here is that why do we have a plant D anyways? Why do we have a plant that has no fertilizer? And the reason for that is because this is actually what's called our control. And the control is basically a baseline comparing if the fertilizer is helping at all. So maybe, like, let's say plant D, if it wasn't 10 centimeters, let's say it was actually like 16 centimeters. That means that the fertilizer A is probably doing absolutely nothing to help the growth. But if we compare just plant A to plant D grew only 10 centimeters and plant A grew 16 centimeters. You could say plant A definitely had a beneficial effect, or the fertilizer had a beneficial effect on plant A. And just by looking at the data, all the fertilizers helped the plant grow. So one thing that we can analyze from the data is, yes, fertilizer does help plants grow, and we know that because uh, based off of this baseline, this control plant D over here, where no fertilizer was applied. All right, so plant D was our control, where it's our baseline of comparison. So let's go ahead and talk really quickly about these two terms, the independent variable and the dependent variable. If you've done the scientific method before in middle school or elementary school, these are probably things that you've covered before. But the independent variables and the dependent variables are going to be present in um, all of the experiments that you're going to do in the future. So the independent variable is the thing that you have the freedom to choose. If you kind of associate the word like independent with Independence Day, what do we celebrate on Independence Day on July 4th? Well, we celebrate our freedom from the British, where we actually became our own country. So the word independent means you have the freedom to choose that, you are alone to do that. So what is the thing that we are controlling in this experiment? It's the type of fertilizer. Okay, you cannot directly control the height of the plants. The plants are going to grow at their own pace. The plants are going to do their own thing depending on what you give them. So you can't just say, all right, I'm going to make this plant grow exactly 16 centimeters, or I'm going to make this plant grow exactly 14 centimeters. That's not how it works. So you can influence the height of the plant based off of what you change. So if you are changing something, like in this instant we're changing the fertilizer type, that's the independent variable. So kind of remember it like this: for independent, I have the responsibility, or I have the power to change what is going on here. The dependent variable is what depends on the independent variable. So the height of the plants depends on the independent variable, or the height of the plants depends on the fertilizer type. If you ever get confused with figuring out what is the independent variable or what is the dependent variable, just ask yourself two questions. Okay, the first question is, does the height of the plant depend on the fertilizer type? And then the second question is the opposite: does the fertilizer type depend on the height of the plant? And one of those is going to sound kind of ridiculous. So that second question, does the fertilizer depend on the height of the plant? That's like saying you went out to your garden, you measured your plant, and today it was 16 centimeters. That means you got to go to Home Depot or Menards and buy fertilizer A. That sounds ridiculous. So if that doesn't make sense, the other one makes more sense, and it's true. Uh, the one that you are changing is the independent variable. Just keep that in mind. So let's go ahead and pause here for a little bit, take a little bit of a break, and I would like for you to discuss with your table, or maybe work on this on your own. Just taking a look at practice problem number 9, and we're going to answer a couple of questions from this. But let's just establish a scenario here. Some students grew sunflower plants in their school's biology laboratory. The following table and the graph show the conditions and the results of the experiment after 3 weeks. So we've got a nice little chart and a graph here to kind of analyze the data. What I would like for you to do, maybe on your own for the first minute or two, and then maybe discussing with your table mates what is going on here, and figure out what is the control, what is the dependent variable, what is the independent variable. Just go ahead and answer all of the questions for practice problem number 9. So go ahead, and I'm going to pause and take a moment here. Okay, so hopefully you were able to answer these questions on your own first, and then discuss them with your table mates. We're going to go ahead and go over this, but I'm just going to go ahead and come back here as we wrap up this practice problem and this set of notes. The first question is, was this a controlled experiment, and why? So we have to first take a look at all of the things that are presented to us in the graph and in the chart. Plants A, B, and C, let's just assume that these plants are the exact same type of plant. Okay, so it doesn't matter what the plant is, but let's just say they're all the same type. We have a lot of things going on here. We have temperature, humidity, water, light, and color of light. Temperature looks to be the same for all 3 plants. Humidity is the same for all 3 plants. Water and light are both the same for all 3 plants. And then the color of light is the only thing that is different. So, was this a controlled experiment? Yes, it was. It was definitely a controlled experiment. And the reason for that is because all of the variables are controlled. And we know this because all of the values are the same for temperature, humidity, water, and light, except for one thing, and that's the one thing that you're testing. So in this case, we are testing the color of light and its effect on plant height. Okay? So this was definitely a controlled experiment. So we're going to go ahead and state a possible hypothesis for this experiment. Now, this next part wasn't necessarily written in your notes, on your guided notes, but for a hypothesis, almost always we're going to state it as this format. If blank, then blank. So a hypothesis is always written like that. If this thing happens, then this other thing will happen. Okay, so you can come up with a different hypothesis here, but I came up with two possible ones based off of this experiment. The first one that I came up with is if I give the plants different colors of light, then they will grow differently. That's just a very broad, wide hypothesis saying, I don't know which color is going to be the best. I just know they're going to grow differently, or I think they're going to grow differently. Let's assume you already knew that different colors of light will affect different plant heights, but you want to know which color is the best. Then you can come up with the second hypothesis over here that I have. If I give the plants different colors of light, then the plants with the violet light will grow the best. Okay, so that's a little bit more specific. That's based off of your background knowledge. Remember, if we go back to the very beginning of the scientific method slide that we had at the beginning of the notes, where the second point was gather information. You've stated the problem, now you're gathering information. Based off of information, if you knew that the color of light affected plant growth, you want to find out which one's the best. That second hypothesis would be a better hypothesis for your experiment. So the next question is, which are the dependent and independent variables? So what are we testing and what is it affecting? That's basically what this question is asking. What are we testing and what is it affecting? We are testing the color of light on the plants, and what is it affecting? It's affecting the plant height. So which one of those two are we in charge of? Are we in charge of how tall the plant is growing, or are we in charge of the color of light? In this example, we are in charge of the color of light, therefore that is the independent variable. I just abbreviated it as IV, and that might be something that you would want to do in the future on a worksheet or something, or even in future science classes, IV and DV. Most science teachers will understand what that means instead of having to write out those big words. So the independent variable is the color of light. The dependent variable is the plant height in centimeters. And then which ones are constant in this example? What are the constant variables? Everything else that's listed here. Temperature, humidity, water, and light. Okay? So everything else that's listed here is going to be a constant variable. Did the experiment prove that the hypothesis stated before was correct? Well, technically, yes. But in science, we don't like to use the word correct or incorrect to describe a hypothesis, because correct and incorrect implies that it's a certain thing, that we have absolute certainty that nothing else was involved in the experiment, and that definitively what we have concluded is what's causing the results. In this case, do we know definitively 100% that it was the fertilizer affecting the plant height? Maybe there was some kind of irregularities in the soil. Maybe there was different types of water being used, tap water versus bottled water. Who knows? So we don't use the words correct or incorrect because there are chances that there is human error involved in the experiment, and that there might have been something else at play that affected the plant growth. But we do use the words supported or rejected. We assume for the best, we hope for the best, that nothing went wrong in the experiment. There are ways you can test for that with math later on. We'll talk about that, but in this example, we're not going to do that. In this case, we are going to say that our hypothesis was supported, that different colors of light do affect plant growth, or that violet light was the best at growing the plants. All right, so that concludes Unit 1, Notes 2 on the scientific method. There are two assignments based off of this in Canvas that I would like for you to take a look at. The first one is just the first one that we're going to work on today, and the next one we'll work on next class period. But the first one is called the scientific method flowchart. It looks like this and should be pretty easy to fill out based off of what you have learned today in class. You can take a look at your notes as well. Just fill in the blanks as best as you can and then submit this in Canvas. So there is a submission for it. If you have forgotten how to submit something or you still haven't quite figured it out, again, there are two documents you can take a look at: downloading a PDF and then annotating and submitting from PDF Expert. So those are two great forms you can take a look at. If that doesn't help you, please at this point ask a teacher, a friend, someone at your table, someone at the tech office how to do that so that you can kind of get familiar with that, because this is something that you're going to be doing several times a day throughout your entire high school career, submitting things through the iPad. So definitely getting that down is important. So complete right now the scientific method flowchart, and then next class period we'll work on this other worksheet called the controls and variables worksheets.